chapter 5, section 3, which deals with the multiplication of events, the multiplication rule for independent events. So we're going to first of all have to identify what are independent and dependent and how that affects things. So in the prior section, just to kind of give you a quick recap of where we're at right now. In the prior section, we had the following idea, that if we had event A and event B, and we wanted to find the probability that event A or event B occurs, then we found this general rule, which is that we have to find the probability of event A plus the probability of event B, but then we have to subtract the probability of event A and event B occurring at the same time. Right, so that's where we were at yesterday at the end of class. Event A and event B, what's the probability of event A or event B happening? So we have to find them individually, but then we have to subtract off the overlap, right? The probability that they both happen at the same time. And then we also considered a little subcase of this, was that if event A and event B are disjoint. Disjoint means that they have no outcomes in common, right? They're completely disjoint, they have no outcomes. They can never happen at the same time, that's what that means. So therefore, this is 0, right? Because they can't happen at the same time. They don't have any outcomes in common, good? So just a real simple little example. Let's say we were rolling a 6-sided die and we're just putting money down on something. So event A, let's say that it's the numbers 2 and 3. I put money down that they're going to roll a 6-sided die and it's either a 2 or a 3. And my friend, event B, my friend says it's going to be a 6. That's all they got. They got a number 6 on there. So this represents our entire sample space. It could be a 1, a 2, a 3, a 4, a 5, or a 6, right? Those are the 6 possible results. This is event A, this is event B. In this case, these two events are disjoint, right? They have no common outcomes. There's no way that they're both going to happen at the same time. So in a case like that, this is 0. When we have two disjoint events, then the probability that event A or event B happens is just equal to the probability of event A plus the probability of event B. This part just becomes 0. Good? So in this little case, what's the probability that I'm going to win? 2 out of probability that event A happens in this little example over here is equal to 2 out of 6, right? 6 total outcomes, and there are 2 ways that event A can happen. So that's 2 out of 6. What's the probability that event B happens? 1 out of 6. There's only one way my friend could win, right? So what's the probability that I win or he wins? A or B. The probability of A or B is equal to the probability of A plus the probability of B. So this is going to be equal to 2 out of 6 plus 1 out of 6, which is equal to 3 out of 6, which is going to be a half or 50%. Good? Yes? Yes? Okay, or we can just count things. The probability of A or B, since we have the benefit of this nice diagram, we can just say me or him. 1, 2, there's 3 ways that either I win or he wins. Good? Good, good? But now, in some cases, there is an overlap. In the cases where there is an overlap, then we might have to use this situation. So this is a case where they're disjoint, so we only have to use the more simplified case. But let's say we have a slightly different case. Let's say that instead of this, we have that I bet on the numbers 1 and 3, and my friend bet on the numbers 3 or 4 or 6. Okay, so he put 3 wages down, 3, 4, or 6. I only bet the number 1. So what are the ways that both of us lose? Well, maybe the number 2 comes out, right? That's not, nobody bet on that. Or the number 5. 1, 2, 3, 4, 5, 6. So we got them all. One 6-sided die is rolled, and I'm betting it's either a 1 or a 3. My friend is betting that it's a 3, a 4, or a 6. Okay, so now if we want to find the probability of A, well, that's still 2 out of 6. Right? 1, 2, there's 2 ways that A could happen. The probability of B, now that's going to be 3 out of 6. There are 3 ways that that can happen. So now we have to think about the probability of A or B. If we did it this way, if I did it right now, I would end up with 2 out of 6 for here, plus 3 out of 6 for there. Right? And so I would end up with 5 out of 6. But looking at my Venn diagram, I know that's wrong, because this is only 4. So how can I get 5 out of 6? I know the answer should be 4. 1, 2, 3. There are 4 ways in which either I win or my friend wins. So I need to take care of this guy. That's the problem. There is an overlap. There is a way that both of us win at the same time, and I'm taking that into consideration twice. This 3 right here has been counted as part of this 2. 3 is in there, right? And then the 3, rolling a 3, is also part of here. I counted it as 1, 2, there it is, and then 1, 2, 3, I counted it twice. That's why I have to subtract the probability of A and B. And the probability of A and B happening at the same time, both A and B happen, well, there's only one way that can happen. The number 3 is rolled, and so there's 1 out of 6 ways in which both of them can happen at the same time. We're good? We're good? Okay, so then that means I have to apply this rule, because these are not disjoint. There is something in the overlap. And so this formula is going to require us to subtract minus the probability of A and B, which is going to be minus 1 over 6. And so now we'll get the answer I expected. 4 out of 6. Which we can just count, right? 1, 2, 3, 4. There's 4 ways that either A or B happens. Any questions? No? Well, you might be wondering, why bother with this whole crazy stuff when it's just easy to count things, 1, 2, 3, 4. Well, if you have the benefit of a nice, pretty Venn diagram, if things are simple, go ahead, ignore all this, just count them. 1, 2, 3, 4. There you go, that's how you do it. Or the probability of A and B happens, well, it's right there. There's only one way it can happen. I'm just counting things. Great. Okay, the problem is that things get complicated, right? So you won't always have the benefit of a nice, pretty, simple little Venn diagram to be able to organize things and know how they go. Sometimes you'll have word problems or other situations where you're going to have to count on this formula to get you through it, right? Good. So there might be some word problem, for example, something like the probability that a random, the probability that a high school student drops out of high school is 20%. The probability that a high school student has a drug problem is 13%. The probability that a high school dropout is someone that has a drug problem is 14%. What's the probability that a student is a dropout or has a drug problem, right? So that's kind of a word problem. There are 1, 2, 3, 4 things in this equation that can give you a word problem where 3 of them are given and the other one is what they ask you for. So they could say the probability that a student a person is a high school dropout and has a drug problem is 13%. The probability that a high school student is a dropout or has a drug problem is 17%. The probability that they're a high school dropout is 14%. What's the probability that they have a drug problem? Right? So 4 things, 3 of them are given to you, 1 of them is missing. We need to rely on that formula. Got it? Good, 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 good. Okay, so this is what we were working on the prior one. Now in this section, we're going to focus a little bit more on this one. How to find the probability of A and B. Again, if you have a nice Venn diagram, easy. Just count them. It's right there. 1 out of 6, done. Okay, but what if you don't have that? If you don't have a Venn diagram for it, or we're just going to dive deeper into it. Okay, so that's what we're focusing on. Finding the probability of event A and event B happening at the same time. Yeah, question?
So the final answer would be P, A, or B or 6?
Oh, yeah. So then you turn that into a decimal, right? What's 4 divided by 6? Is that the 66%, 66.67.
Okay, so like you don't separate it like PA is this, PB is this, PA and B is this, but the final thing is PA or B equals the 66.
So this is the application of our formula. P of A or B is P of A plus P of B minus P of A and B. So this is this, and this is this. We found those separately. But then when we add these, they all have the same denominator, so that makes it easy. This is 5 minus 1 is 4 over 6, which turns into that. So the probability of A or B is 66.7%. Good. Any other questions about that? No? Okay, so we're focusing our attention on this in this section. Probability of A and B happening. So when you are trying to find the probability of two events happening, there are two general things that we have to think about. Whether these two events are independent or whether they are dependent. So we're going to start thinking about that, what that means, looking at the definitions, looking at some examples, so that we can look at a situation and determine if we are in the world of independent or if we are in the world of dependent, because the formulas are different for them. So let's look at some. Let's look at the definition for it. So two events, E and F. Oh, okay. Well, let's just work with E and F like they have there. Instead of A and B, E and F. Two events, E and F, are independent if the occurrence of event E in the probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of the event E in the probability experiment affects the probability of event F. So that's the exact definition for it. I think that perhaps at this point it's kind of hard to really sink your teeth into that and really think about what that means. So we'll look at some examples and we'll refer back to this down the road and maybe it'll make a little bit more sense. So first of all, let's look at some examples of different cases where they're dependent or independent. So let's consider this. Suppose you draw a card from a standard deck, right? You got a 52 card deck, 52 cards in here. We're going to randomly pick one out of it. And also we have a die, a 6-sided die. We're going to roll that. And so event A is draw a heart. And we pull this guy out, we draw a heart. Boom, like there, I pulled out a Jack of Hearts. So this would be a success. Or we roll it and we roll a even number. We roll our die, we roll an even number. Those two events, are they dependent or are they independent? Let's go back to the definition. Two events, E and F, are independent if the occurrence of event E in the probability experiment does not affect the probability of event F. Do you think that that's the case here? So let's say event E is draw a heart, and event F is roll an even number. Does your selection of a card from a deck of cards get affected by what you rolled? No, they have nothing to do with each other. They're completely separate. Okay, when you're rolling this guy, if I told you, you know what, it turns out that you did pull out a red card, you did pull out a heart, does that affect your roll? Not really. Or if it turns out that you did roll an even number, does that affect whether you pull out a heart card? Doesn't affect it at all. So they're definitely independent, right? One thing does not affect the other at all. Good? Other situations, how about die on a plane? The probability that you die on a plane and the probability that you win the lottery, are they connected to each other in any way? No, right? They're clearly separate, independent things, right? If you were on an airplane and it starts shaking, you get a little nervous, so that's a lot of turbulence. What is that, a weird noise from the engine? What's happening here? Do you look to the person next to you and go, wait, have you won the lottery recently? Oh my God, this plane is doomed. No, they have nothing to do with each other, right? Okay, so if you want to find the probability of, we'll get to the formula in a little bit. So those two things are definitely independent. Look at another case. How about, suppose the two 40-year-old women who live in the United States are randomly selected. The event woman 1 survives the year and the event woman 2 survives the year are also independent. Okay? So two 40-year-old women are randomly selected, and we want to look at their probability that they survive the year, or the event woman 1 survives the year, woman 2 survives the year. Woman 1 survives. Number 2 survives. Okay. So the likelihood, or whether event 1 occurred or not, whether event E occurred or not, has nothing to do with the other one, right? So if two women are randomly selected from the United States, and it turns out that maybe the first person did not survive, does that affect the survival of the other woman? As long as they're completely randomly selected, it shouldn't have any effect on it at all, right? Now, how can we change this to something that is dependent? So right now they're independent, but it entirely hinges on the fact that they're completely randomly selected. If they weren't really randomly selected, if there was some sort of connection, then maybe they might be dependent. So for instance, if instead of being completely randomly selected, this was like a sisters thing. Two sisters are randomly selected, and it turns out that, okay, let's even say twin sisters. Two twin sisters are randomly selected, and it turns out that one of them died the first year. Does that affect the likelihood that the other one will die? Maybe, right? What would be a really important question? How did they die, right? That might affect things like, what if she died of a genetic disorder, some sort of heart thing, right? That, oh man, you're in trouble, right? So it doesn't guarantee that the other one is also going to die, but it might affect those chances, right? How about if they weren't related, but maybe they lived in the same building? Right? Two women are selected, they both live in the same building, one of them died. Does it affect the likelihood that the other one will die? How did they die? Alright, so she died of a house fire. Alright, the other one lives in the same building. I don't know. You know, it doesn't guarantee one thing or the other, but it affects the likelihood, right? It gets affected. Your thoughts about whether this woman survives or not get affected by the new knowledge that this one died in a house fire and this one lives in the same building. I don't know, was she home at the same time? What floor do they live on? All kinds of things come into place, right? So if they're not randomly selected for the United States, there might be some sort of connection, therefore there might be dependent. The result of one might change your opinion about what the result of the other one is. Good? Questions, comments, issues? No? 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 Okay. We're first going to consider the case where they're independent. So when two events are known to be independent, when you read your word problem, you establish this is the case where they're independent, then the rule is really easy. Here it is, the multiplication rule for independent events. If E and F are independent events, then the probability of E and F is equal to the probability of E times the probability of F. All you have to do is find them separately, multiply them together. That's the probability that they will both happen. So going back to the lottery and the airplane, we know that those are independent. Dying on an airplane and winning the lottery, you know, the big jackpot. I'm not talking about the, you won $10 or something. Winning the big jackpot and dying on an airplane crash. Those two things are definitely independent. They have nothing to do with each other. So the probability that both will happen, that you do win the lottery and you also die on an airplane, well, we find those two things separately. We find those two probabilities separately, independent of each other, and all we have to do is multiply them together to get the probability that both will happen at the same time. Good? Okay. So for example, the probability that a randomly selected female aged 60 years or older, that person will survive the year is 99.186%. What is the probability that two randomly selected 60-year-old females will survive the year? Okay, so probability that one survives the year versus probability that two will survive the year. So we have that probability that woman number 1 survives, and we want woman number 2 to survive. That's what we want to find out. Probability that 2 randomly selected women and both of them survives. Woman 1 survives and woman 2 survives. Well, these 2 are independent as long as they're completely randomly selected from the United States. If they were connected in some way, they were related, or they have some sort of association, like maybe they both went to the same school, they both worked in the same place, they both have the same, maybe they both belong to the same like high diving club or skydiving club, something along those lines, then when you find out this one died, then, it might affect the likelihood that the other one died as well, because there's potentially some sort of connection. Yeah,
if they are like randomly selected, but there happens to be like something that does connect them, then does that make it dependent?
No, when you are in the process of selecting, that part has to be random. So if you truly randomly pick 2 people, and it just so happens that there's some sort of connection, then it doesn't matter anymore. It doesn't convert it into a dependent case. You went through and you randomly selected them, and if there happens to be some connection, then that's not something that affects it. Does that make sense? So truly random means that you write down everybody's name on a little piece of paper, right? Put it all in a giant hat, and you shake it all up, and you reach in there and you pick 2 names. And once you've done that, if there happens to be some sort of connection, they're both women, or they both go to the same, the same gym, or they both, right? There could be some sort of connection, but that doesn't matter. You went through the process of randomly selecting it from the giant pool, so it's randomly selected. Got it? Good. Okay. In this case, because they are independent, to find the probability that one and the other, then this is equal to the probability that woman 1 survives times the probability that woman number 2 survives. Right? Because they're independent and we want both of them, 1 and 2, to survive, that's equal to the probability that woman 1 survives times the probability that woman 2 survives. And they're both going to be the same in this case. The probability that a woman survives, any woman, the year, is equal to 0.99186 times the probability that the second woman survives. It's the same thing, 0.99186. So we just multiply those 2 together, and we get 0.9838. Good. So the probability that both will survive is equal to 98.38%. Good. What's the complement of that? So what would be the opposite of this then? Either both survive, and what's the opposite of both surviving? Both die? There could be the other case, right? One dies, right? So the opposite could be that maybe this one died, or maybe this one died, or maybe they both died. So there's 3 other cases to think about when it's the complement of they both lived. Good? Questions? Okay. So here's another example. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. If there is a 1-year warranty on the equipment, what proportion of customers will actually make a valid warranty claim? That's an interesting one, right? So they know that a lot of their products are defective. 10% is a pretty high number of products that are broken, but maybe they're too lazy to fix them, or they just don't care, whatever. They're just letting them go out the door that way, even though they know 10% of them are broken. because they know that a lot of people don't really use them in the first year. So therefore, some people are going to get a defective one, but they never even tried it in the first year, so they're not going to have that opportunity to return it and get their money back. By the time they finally get around to using it, it's going to be too late, right? The warranty has expired, and they're not going to be able to make a valid warranty claim. Good. So in order to be able to get a valid warranty claim, two things have to happen. One, you have to get a defective product, and two, you have to be a person that actually uses the equipment. So, probability that a valid warranty claim, probability of a valid claim means that two things happen. You get a defective one, defective product, and you use it. Use the product in the first year. Those two things have to happen in order for you to have a valid claim and therefore potentially go and ask for your money back. Right? This is an and statement. Now, are they dependent or independent? So, the people at the factory doing their thing, or the actual material being, defective, whatever, does that have anything to do with whether or not you're the kind of person that buys something online and then receives it and never really use it? So, being this kind of a person and whether or not the product is defective are completely independent, right? One has nothing to do with the other. Right? So the probability that they both happen at the same time is going to be equal to multiplication. Is going to be equal to the product being defective times the probability that you use the product. Okay? So they gave those to us. The probability that it's defective, we know that that's 10%. 10% of all their equipment is defective, and we know that through research, we know that 30% of our customers don't even use the product. Only 30% of the customers will actually use the product. So 0.3. Shameful. So they're saying 70% of their clients buy it and then they don't even use it. I'm going to work out tomorrow, stick it under the bed, and tomorrow I'll work out, and they just never really do. Okay, so the probability that you have a customer that has a valid claim is going to be equal to the product of these two, and what is that equal to? Or 3%. So even though they have 10% of their products going out the door that are defective, really only about 3% of their products are going to come back with a valid warranty claim. Any questions? So now if we have a chain of events, if we have a bunch of different things, so here's the multiplication rule for n independent events. If e sub 1, e sub 2, e sub 3, all the way out to e sub n are independent events, then the probability that E1 and E2 and E3 all the way out to E sub n occur all at the same time, and remember this is where they're all independent of each other, well then all we have to do is find all those probabilities independently and then multiply them together. And that's how we find the answer. Okay? Good. Questions? So here we only have two. In this case, there's only two. But if we had many of them, we would just find them all separately, independently, and then multiply them all together. Good? Questions? Okay, so here's an example. Back to the survival rates. The probability that a randomly selected female aged 60 years or older will survive the year is 99.186%. What is the probability that 4 randomly selected 60-year-old females will survive the year? 4 of them. What's the probability that 4 will survive the year? Okay, so alright, so So this is going to be probability that woman 1 survives and woman number 2 survives and woman number 3 survives and woman number 4 survives. Okay, that's really long, but we have 4 different things here. We have this one, and this one, and this one, and this one. 4 different things. We want all 4 to happen at the same time. Notation-wise, as you can see, it's really long. So you can start to come up with shortcut notation that makes sense to you. So, for instance, right now we're clear that we're talking about survival, so I don't think it's really necessary for me to put survive every single time. So we could do like shorthand notation and just say W1 and W2 and W3 and W4. We could do that. Or we can even just put 1, 2, 3, and 4. You just have to be clear about what your notation style is describing and, don't forget things. So now we have 4 different things. They're all independent of each other because they were all randomly selected. So I know that this is going to be equal to the probability that woman 1 survives. I'll put woman 1 survives times the probability that W2 survives times the probability that W3 survives times the probability that W4 survives. Okay, so now all 4 are identical, so this is really going to be equal to 0.99186 times 0.99186 times 0.99186 times 0.99186. Right, they're all independent, so we just multiply them together. And of course, the shorthand for this is just 0.99186 to the power of 4. And now we can just get our calculator and figure out what that is. So I'm getting 0.9678 or 96.8% chance that that will happen. Any questions on this? I think the writing and the notation is probably harder than the actual math. So back to these females. The probability that a randomly selected female aged 60 years or older will survive the year, 99.186. What is the probability that at least one of 500 selected 60-year-old females will die during the course of the year? Okay, that's the question. What is the probability that at least one of the 500 selected females will die during the course of the year? So be careful with the change of words here, the survive versus the die. They're complements of each other, right? You either survive or you die. But we have to be careful about which one they're asking us and which one they're giving us. So first of all, let's try and think about the sample space for this. What are the possible things that can happen when 500 randomly selected women are chosen, and we want to look at whether they survived or died? So depending on which one you want to stick with, you can either look at it from the perspective of how many died, or you can look at it from the perspective of how many lived. Since they're asking me about how many will die, let's look at it from that perspective. So the possible things that can happen is that 0 women die, or maybe 1 dies, or maybe 2 die, or 3 die, right? All the way down to like 499 out of the 500 die, or maybe all 500 die. Okay? That's the sample space of all the things that could happen. Does that make sense? Are these are the outcomes that can happen, right? So they're all disjoint events. If 500 women are selected, and we just sit around and wait for a year and see how many of them died, after 1 year, either 0 of them died, right, which means all of them lived, or maybe 3 of them, exactly 3 of them died, which means 497 of them lived, right? And we can't have more than one happen at the same time. We can't say after 1 year 3 died, but also 499 died. That doesn't happen, right? So these are all disjoint. Keep that in mind. So we want to know the probability that at least, probability that at least one of the 500 randomly selected 60-year-old women dies. So we want to find this. Find the probability that at least one died. This is the compound event that's made up of lots of these outcomes, right? What kinds of outcomes satisfy that? Right? In other words, like if I was betting money that at least one was going to die, and I went around and like, oh, yeah, 3 died, so yep, it satisfies that statement, right? Or 2 or 1, right? All of them really satisfy it except this one. That's the only one that doesn't satisfy that statement, right? At least 1 means 1 or 2 or 3 or 4 or 5, all the way out to 500. Good? Okay, so there's 2 ways to find this. The first way is to recognize that this is the same thing, or is equivalent to the probability that exactly 1 dies, or exactly 2 die, or, right, we keep going, exactly 500 die. Right? In other words, all of these individual outcomes satisfy it, and these are all or statements. Or. Is everyone with me still? Right? They're all disjoint, so if I want to find the probability of this, or this, or this, or this, or this, I'm going to have to add them all up. I have to find them all individually, and then add them all up. So then I'd have to find the probability of exactly 1 dies, and then I'd have to add it to the probability that exactly 2 die, plus plus the probability that all 500 die. That's really nasty, really ugly, because even to find this, exactly 2 die, now we have to think about the order of things. Was it the first 2 that died? Was it the last 2 that died? The middle 2? It's getting really, really, really nasty. So we don't want to head down this path. We want to think of a different way of getting to it. And so what we're going to do is go back to the drawing board and think about this. Since this was our sample space, and all of these constituted all the simple events, then what do we know about the probabilities of all the simple events in our sample space? They all add up to, they have to add up to 100. So the probability of this, the probability of that, all of that has to be equal to 100%. Good? So I know that the sum of all these probabilities adds up to 100%. So instead of finding all of these individually and then adding them together, wouldn't it be a lot easier for me to just find this one, just 1, I don't have to find all of them, just 1, and then I know that this plus all of this, right, all of this constitutes at least 1. All of these are at least 1. So if I can just find this one right in here, then I know that this one plus this one has to be equal to that. So in other words, the probability of getting 0 die plus the probability of getting at least 1 has to be equal to 100%. Everyone's with me? Yes? So the probability that 0 die plus the probability that at least 1 dies has got to be equal to 1. Because together they constitute everybody in the sample space. Right? This is the first one, this is everybody else. Good? And we were looking for this one. So now, simple algebra, all we have to do is take this guy over here, and that gives us this. So the probability that at least 1 dies is equal to 1 minus the probability that 0 die. So now I only have to calculate one probability, instead of having to calculate, you know, these 500 of these. Yes. Yes. Right. Anytime you have two events such that together they make up the entire sample space, we call them complements of each other. So none and at least one are complements of each other. Great observation. Anything else? We're good? We're good? We're good? We're good? Good, good, good. Okay, so now what you just got to do is find this. Find the probability that 0 out of the 500 died. What's another way of saying that? That all of them survived, right? All 500 survived. 0 died is the same thing as all 500 survived. And if all 500 survived, well, that's going to be equal to, let me put it on this board now. So we have the probability that at least 1 dies is equal to 1 minus the probability that all 500 survive. So this is equal to 1 minus the probability that the first woman survives and the second woman survives and all the way out here, the 500th woman also survives. Does that make sense? All of them survive. How does that happen? Well, the first one survives, and the second one survives, and the third, and the fourth, and the all the way out to the 500th one. Everybody survives. That's the only way that we can get this statement, the probability that all 500 survive. Okay, and now these are all AND statements. Right? These are all AND statements here, and we know that they're all independent of each other. And statement, and statement, and statement. And they're all independent of each other, so all we have to do is multiply them together. So this is equal to 1 minus, I'll put a big bracket here so I have to figure this out. This is the probability that first woman survives times the probability that the second woman also survives times times the probability that the last woman also survives. Good? Okay, so now there's 500 of them. This is equal to 1 minus 0.99186 to the power of 500. So I'm getting 1 minus 0.0167953-ish, and then 1 minus that is equal to 0.9832. Okay, what does this mean? The probability, if we take 500 randomly selected women, 60 years or older, the probability that at least one dies, there's a 98.32% chance that at least one dies. Maybe 2 die, maybe 3 die, maybe 74 die, I don't know, but at least one or more, there's a pretty high likelihood. Okay? What does this number represent? This represents the likelihood that all of them survive, which is only a 1.67% chance that all 500 will survive the year.